fractal infinite image theory, that thing. Why is it backwards? Does it look backwards? It's backwards.
Is it? It's a little bit backwards. Hey, Dr. Blake.
Yeah.
So in Block's book, he mentions I haven't read the book that much, but because I use Jim's book, and Block's mentions a topic called perturbation method. Can you explain what that is?
For waveguide loss analysis, we'll go over that today.
Oh, okay.
Perturbation method basically assumes that when you add loss to the waveguide walls, for example,
Yeah.
that the fields are only slightly perturbed from the lossless case. So then you can utilize the modes of the lossless case that you derived before, along with the sheet impedance that represents the loss in the metallic waveguide walls, in order to derive an attenuation constant for
Okay.
the field decay.
Okay, that makes sense. That phrase now makes sense. Because I've read it.
So perturbation can mean a lot of things, right?
Yeah.
That term for a lot of different concepts, but at least there is in the one that we're going to study in this chapter, is referring to keeping the original modes that we derived from lossless walls, for the lossless waveguide, when we analyze the loss of it. How you doing?
Okay.
For all that all. And words, she wants to keep these printers out of paper. You know, I don't think men, but the guys prompting to grow up.
What?
He's just exclusive prompting people. No, this is on the other side. So he prints out a whole chapter of.
How's it going?
It's going, how are you?
Good.
Pages, front and back. Yeah, you ran this out of it.
Just
He's not tired. That's fine.
So on the graph where we have the normalized frequency, what does it mean when we have the reactive impedance?
So
when it's less than as a cutoff frequency.
you're below the cutoff frequency, reactive impedance. If you were to calculate the pointing vector in the direction of travel, you would find that, that there's no real power flow, right? And that's also reactive impedance. Also, if you have a reactive impedance, then that means E and J are not in phase, right? So, or sorry, not E and J, E and H. So if they're 90 degrees out of phase, then that can imply.
Does it also mean evanescent or no?
Yeah, it's associated with evanescent phase, right? The Z direction. We'll see some more of that today.
She doesn't have cell service. Facebook. I use it for the parts. Don't tell my mom.
How's it going?
Good, how
Good to see you, good to see you. Joe Baker or? Joe Baker? Very nice. I like that.
Yeah, you did a great job.
Oh, yeah, I need to. I always forget that. The game was a lot smaller. These batteries are always almost dead.
Oh, yeah. Oh, yeah, I remember. The restroom.
How's it going?
Sorry, that's not probably so good.
Okay, so it's 4 o'clock. Let's go ahead and get started. All right, so what are we studying? We're studying rectangular waveguides. You've probably seen these before, but I'm trying to provide a little bit more in-depth, visualizations of the results and understanding of things. So I've tried to sprinkle into some different topics that you might not normally see in your first glance at rectangular waveguide studies. So what have we been studying before, or what did we do last lecture? We looked at rectangular waveguides and the modes that they support. Just as a quick review, we derived transverse electric modes by assuming an electric vector potential that has only a z component, because if we take the curl of f, we get d, or negative curl of f, we get d, and that means the electric field, therefore, will be orthogonal to z, and hence will not have a z component. So it'll be transverse electric to z. And then we can find the associated H from that solution for E. Okay, we got the modes, we applied boundary conditions, and we looked at the dispersion of the waveguide for each of these different modes that appear as we increase the frequency. And that basically comes from this equation here, right? Beta z squared is beta squared minus beta c squared. When beta z is the propagation, or the propagation constant in the phase constant in the direction of propagation, right? So if beta z is a real number, then you have propagation along z. If it's imaginary, then it's evanescence, right? So what we have here, if you take the square root of this, so beta z could also be the square root of all of this, right? Beta z. And we can see that this number that we're subtracting from beta, which is fixed, omega squared root of mu epsilon, right? Omega squared mu epsilon in this case, because it's beta squared. So we know the frequency, we know mu and epsilon of the material filling the waveguide. So this beta squared is fixed. As we increase the mode order, m and n are increasing, this number becomes bigger and bigger. And at some point, we're gonna subtract a number larger than beta, right? And therefore, this beta z will become imaginary. Yeah? Let me think about that. Yeah, when you get to higher order modes, then they can become evanescent, right? Beta z square root, yes. Very good. That's correct. Okay, great. And we have transverse magnetic modes. We derive these assuming that we have only a z component of A and no F, and we take the curl of A to get B. So the magnetic field then is orthogonal to Z, and that gives you transverse magnetic to Z modes, and we can find E from H using Maxwell's equations. All right? We looked at the modal impedance. The significance of the modal impedance is that at the cutoff frequency, we have for TE modes an infinite impedance, and for TM modes, we have a zero impedance. And above the cutoff frequency, we have purely resistive wave impedance. E over H is resistive, right? Just like free space, E over H is 377. Below the cutoff frequency, the impedance is reactive, indicating no power flow in the direction of propagation. we looked at the modal fields, right? So we derived the mathematical expressions directly from Maxwell's equations that describe these vector fields in the cross-section of a waveguide. So any cross-section of this waveguide, we're assuming it's infinite, right? Remember when we derived the modes, we said there were no discontinuities in the z direction. All the discontinuities were x and y. Therefore, we have traveling waves along the z, and that it's infinite if there's no discontinuities. So any cross-section I take in the waveguide is equal, right? So any cross-section is valid. I take a cross-section, I get this modal field distribution, this vector field in the cross-section of the waveguide. Now, this cross-sectional view, or this vector field, does have z-dependence, e to the minus j beta zz. And therefore, each of these vectors are going to vary with z, but they all vary together, right? So the whole vector field in the cross-section of the waveguide will vary periodically. It'll repeat along the z direction, and you get something like this. If you take this modal distribution here for the TE10, and you allow, well, okay, and this is both time and space changing, right? But if you fix time here, if I pause this animation, then I look at different cross-sections. They are this cross-section here. They're just multiplied by e to the minus j beta z, all of them, right? Okay, good. And you can see as you increase the modal index, in this case we increase m. If you increase m, which is the index in the x direction, right? Then you pick up more variation along the x direction. Here we have just one variation, a half sinusoid, if you will, in the cross-section of the waveguide. All the vectors point vertically upward. And in this TE20 mode, we have one whole period of the sinusoid, if you will, representing the amplitude in the x direction, vertically pointed here and pointed downward here, right? And you can get higher order modes like 3-0. Okay, you can do the same thing in the y direction. We have TE01 and we have TE02 here, and then we might have TE03, we do not. And you can vary both of them, right? You get TM11, 21, 21, and so forth, right? TE and TM, right? And you can have higher order modes here where you have a very high frequency or higher order mode, right? Okay, good. All right, and that's kind of where we left off. We started studying the TE10 dominant mode because this is the most common way you'll operate a waveguide is in dominant mode, right? Single mode operation using the dominant mode. All right. So the dominant mode is described, the first mode that appears. If we go back to the dispersion, we can see that the very first mode that appears as we increase the frequency is the green line, which is the TE10 mode, right? And then we keep increasing the frequency, we end up with the TE20 mode is the next mode that appears. And the third mode is the TE01. And then we pick up TM mode, I'm pretty sure, somewhere here. TE11, then TE, oh, I'm only showing TE modes here. Okay, let's not, I didn't plot also the TM modes on there. So TM mode should probably be there soon, right? Should be there in somewhere. So this is only showing the dispersion of the TE modes. I think it's because we only derived the TE modes at this point in the lecture, right? Yeah. So a better plot would show both the TE and the TM modes. Then you can see when the TM appear as well. All right, but for sure, the dominant mode is the TE10 mode. All right. Okay, so if we reduce our equations or specialize into the case of m equal to 1, n equal to 0 for the TE10 mode, we end up with this electric vector potential in z direction. We took the curl of that, and then we used Maxwell's equations to find the h fields associated with the e that you get from taking the curl. We get cosine pi over a times x, e to the minus j beta z. And then we know what beta x is. In this case, we have m equal to 1 and n equal to 0. So when n is equal to 0, we have beta y equal to 0 because it's 2 pi n over b. And beta x was 2 pi n, or pi n over a, right? So in this case, we end up with pi over a. And then we can express beta as 2 pi over lambda. And then we can find what lambda is, which is 2a, which makes sense, right? The wavelength in the x direction associated with this mode is, if you were to extend it, is 2 times a, right? This wavelength. So from here to here, right? Because this keeps going. So this wavelength, lambda x, is 2 times a. for the first mode, right? Very good. Okay. Beta cutoff we find as 2a as well. And then we can find EY, HX, HZ. But we don't have HY, EZ, or EX, right? This is a TE mode. We expect no EZ. But then we also have no EX, right? No HY either. All right, good. So then we looked at these modal field patterns in the cross-section, different various cross-sections of the rectangular waveguide shown in that figure there. All right. So that's where we ended up last class. Okay. Now, we're going to look at the TE10 mode surface current density. So first thing that we can see, right, is that this modal profile here, this TE10 mode is traveling down the waveguide, yeah? So we can expect that the magnetic field, which is associated with it, which forms closed loops around the minima, right, and the maxima. So if this is a maxima coming out of the board of the electric field, this red spot, for example, the next one will be a minima going into the board, for example. The magnetic field circulates about those two, right? So it circulates in between here in the XZ plane. All right. So if we have a magnetic field like that, and it's moving down the waveguide, we expect the current density, which is related to N cross H, to also have a particular pattern that's related to this looping magnetic field, and it also travels down the waveguide, right? So here's what that looks like. I made this plot. I'll show you how to make similar plots. But what I'm showing here is, first let's calculate the current, right? We have a bottom wall and a left wall because it's identical on the right wall to the left and the top wall to the bottom wall. And we can calculate or get a good feeling of what the current looks like by only calculating that for the bottom and the left wall, all right? So the current density, we'll call it J plus for the current density associated with the wave traveling in the plus Z direction, is N cross H, where H is evaluated at the wall, right? And N is the normal pointing into the waveguide on the bottom wall. All right. So what is that? That means it's y hat, right? So this normal vector here, see if I can get a different color. Green maybe. This unit vector N hat is like that, right? For the bottom wall. In general, we have, oh my goodness. In general, we have X and Z components of the magnetic field. So Y crossed with X gives you Z. Y crossed with X gives you minus Z, right? And then Y crossed with Z gives us X, right? So we get XHZ plus minus ZHX plus, all right? We evaluate this at Y equal to 0, putting us on the bottom wall of the waveguide. All right, so if we plug in what we have for HZ and HX from the previous slide, we derive this result here, right? So this one is the first term, X hat, and this one is the second term, Z hat. So on the bottom wall, we have two components, yeah? These two components, one is in the X and one is in the Z direction. And what we can see from these is they're 90 degrees out of phase. This is all real numbers, right? So here first, this all here, these are all real numbers. These are all amplitude terms, and these are all amplitude terms, right? So we have cosine, we have sine, and then we have a J as well. Okay, having that, what you notice is that the electric field vector, or the magnetic surface current, sorry, the electric surface current vectors here at each point are circulating around in a circle, right? Because they have an X and a Y component, sorry, X and a Z component. That X and Z component are out of phase and they're different amplitudes, right? So what happens is the vector will rotate like this due to the out of phase nature of it, and due to the different amplitudes, it's going to trace an ellipse. Each of those vectors, right? Here's a static picture of it that's from your book. And what you can see is that the electric surface current tries to converge at the center of these loops, right? And then in the next loop over, it diverges. And this is a static picture, but you can see that here. Converging spot here goes this way. And then you have the diverging spot, which is going that way, yeah? All right. On the side wall of the waveguide, the left wall, we have J plus equal to N cross H evaluated at the side wall. And that is x hat for the, if it's the left wall, x hat is the unit vector normal to that wall. And we have zhz plus, we evaluate that at x equal to 0 to put us on the left wall. And we get minus yhz plus, and here you only see one component, right? So we can't have anything rotating. We only have one component. We remember that from polarization last lecture, or last semester, right? Where we studied LP, CP, and EP polarization states. In order to get circular polarization or elliptical polarization, we need at least two components, right? Here we have one component, and that one component has a particular amplitude, and it varies with z. So that's what we're seeing here, right? No variation in the y direction. This is not a function of y. So we have a constant along the y direction for the current. Doesn't vary. It is a function of z, so we expect variation along z, but it's only a function of z, right? So that's how we see. If we were to pause this animation, we could see that variation in z, right? Okay, great. Good. So this is an airfield waveguide, WR90, operated at 10 gigahertz in the X band. And what I'm plotting here is the real part of j plus e to the j omega t, right? That's how you get back to the real vector field. Okay, so how do we make these plots? Well, I added the code here for you guys on the next slide. So this is a GIF, right? You can use MATLAB to make GIFs, and maybe you'll want to do that for your own reference, but also for your understanding. Whenever you have say you have a new problem that you derive and you want to sort of understand the dynamics of it, then you can make a GIF that will illuminate or basically show you how, provide more insight into the vector field, right? The dynamics. So here's the code, but basically what I want to tell you is this is the command that's relevant that you probably haven't seen, or maybe you have, GIF. So you call GIF, then you name your GIF, and then you loop through some time parameter, and you'll see these are the exact equations that I derived on the previous slide. Quiver is a vector field command, how to draw these arrows as a vector field. And then you say draw now once you have plotted one frame of your GIF. You draw it, and then you say GIF, and then you loop back, all right? But if you want it to look smooth, then you want to delete these after you store that image in your GIF, right? Okay, cool. All right, any questions on that? I believe it is. I believe that's built-in function.
I tried it and it wasn't in this.
I didn't have to download anything.
Okay, then I'll
Type in the command window, you can type help GIF. That should be a standard command. Maybe I downloaded something a long time ago and forgot. Could be. Okay. So we can also view the TE10 mode as the superposition resulting from two plane waves that are bouncing back and forth within the waveguide as it propagates down the waveguide. You get the exact same solution. As a matter of fact, you can mathematically show that they're equivalent. So here, let's start with the TE10 mode. And I'll tell you why this is a useful analogy or a useful viewpoint later when we talk about how you can use waveguides to extract material parameters or reflection coefficients from infinite arrays based on a unit cell that you plug at the end of a waveguide. Okay, so TE10 mode, we can write that as E plus as a function of X and Z. So it's Y polarized, EY, and that's equal to minus Y hat, and here's the mode, right, that we derived for TE10. Okay, what we're going to do is take this sine function here, and we're going to split it into two exponentials divided by 2j, right? Because of that formula, e to the jx minus e to the minus jx divided by 2j is equal to sine of x, yeah? Okay. All right, well, these exponentials are nice because we know exponentials are associated with plane waves. So we distribute this, or we pull out the 2j, right? So if we pull out the 2j, 1 over j is minus j, we cancel this minus sign, and we get plus j here. Y hat, a10 over 2 epsilon, where the 2 comes over here. And we have pi over a. And then we have these two plane wave terms, right? All right, so let's understand these a little bit better. If we let pi over a equal to beta x, we don't have to let that, right? That is already by definition. Beta x is pi over a for this mode. But we can let beta x equal to beta sine of
gamma, psi, right? Sine of psi. And then we have beta z equal to beta cosine of psi. Then we can write beta x squared plus beta y squared plus beta z squared is equal to beta squared times sine squared of psi, which is beta x squared, and beta squared times cosine squared of psi, which is beta z squared. And what is beta y for this mode? 0, right? There's no variation in the vertical direction. All right, good. So that's equal to beta squared. So we satisfy here the dispersion relation, right? If we make that definition, then beta x squared plus beta y squared plus beta z squared is equal to beta squared as required by the separation relation that we obtained from the separable solution to the wave equation of rectangular coordinates. All right, good. So we can define beta x as beta sine psi and beta z as beta cosine psi. All right? That allows us to get kind of a geometric picture of what direction these plane waves are traveling within the waveguide. Let's take a look at that. So let's plug these definitions back into our EX plus, or E plus rather, EY plus. We can say E plus is decomposed into an E1 and an E2, all right? E1 is jy a10 over 2 epsilon pi over a, same coefficient we see here. And we pick up this first exponential, which is e to the j beta. And then we have pi over a here, which we have set to beta sine of psi. And then we have beta z, which we have set to beta cosine of psi. And we get e to the j beta x sine psi minus e to the j beta z cosine psi, right? Good. Then we have E2 here, which has the same coefficients, but we pick up a minus sign from there. So here's the minus sign, jy hat, same coefficients. And now we have e to the minus j beta x sine psi minus z cosine psi. All right? Okay, good. So let's take a look at this diagram. What are we looking at here? We're looking at the rectangular waveguide. Remember, we have this rectangular waveguide. Goes off like that. We have y here. Whoops. Let me clear this up here. We have the y-axis here, the x-axis here. This is A, and that's B. So what are we looking at when we look at this figure here? We have the z-axis here, right? We have the x-axis here. So we're looking in the xz plane now. The z-axis normally comes out like that. We're looking at basically the bottom or the top wall of the waveguide. All right, so we're looking down above it, right? We're above the waveguide. We're looking down from here, and we're seeing these two plane waves bounce back and forth within the waveguide. And those exactly sum, phasor sum everywhere to give you that TE10 mode everywhere, right? So it's an exact decomposition. So that means that this mode can be viewed as two plane waves. One which is going this way, the dashed line one. The dashed line gives us E2, right? The dashed line gives us E2. And it's pointed down, right? Why is it pointed down with respect to E1?
Y hat direction.
What's that?
Y hat directions.
They're both y hat, right? But why is this E2 pointed into the board with respect to E1, which is pointed out to the board? Why are they opposite?
Minus.
Very nice. There's a minus sign, yeah? Good. So we have two plane waves. One's polarized in the, let's say, minus y direction, E2 in the minus y, and E1 in the plus y direction. And they bounce back and forth like that, right? Okay. The angle that they make with the wall when they bounce is psi, right? Whoops. Is psi. All right, good. So how do we get beta x from here, right? Here's a triangle. So we have a triangle here, right? Here's a triangle like that. This is the angle psi, right? And here we have beta z, and here we have beta x, right? So what do we get for beta x? Beta x, okay, so let's just do this the long explicit way, right? So we have sine of psi, which is equal to opposite over hypotenuse, beta x divided by beta, yeah? Or we get beta x equals to beta sine of psi. Okay, it's kind of sloppy writing because I ran out of room. And then the other one is cosine, right? Cosine gives you beta z over hypotenuse. Okay, cool. So why is that useful? What's the point of us being able to visualize or to describe a TE10 mode in terms of these two counterpropagating, or sorry, they're not counterpropagating. They're propagating the same direction, but they're bouncing back and forth between the waveguide walls in this manner. Because let's say I want to do let's say I design a metasurface or something, or a reflex array, and it's an infinite array, right? It's a common approximation. We put periodic boundaries around the walls of the unit cell, and we have a infinite repeating model to calculate the mutual coupling accuracy, right? So if I wanted to measure, if I designed something like that in simulation, I wanted to measure what the reflection coefficient is in an infinite environment, then I can use a waveguide, and I can, because at the end of the waveguide, so here's a waveguide, right? So we have a waveguide, right? At the end here, I place inside of the waveguide, filling it up, a unit cell, right? Maybe some kind of, let's say a patch antenna. If I just have a small patch antenna and I put the waveguide right on top of it, and then the walls, by image theory, the PEC walls are going to image that patch antenna in both directions, right? So I'll get an infinite array out of that. Does everybody see that? Let me see. Let's say I have a patch antenna right here, right? Here's a patch antenna. All right. If I want to measure this patch antenna as if it were in an infinite doubly periodic environment, then I could just throw a waveguide on top of it, a metallic waveguide like that, right? And these are all PEC, right? It's a metallic waveguide. So by image theory, any current that's induced in here on this patch, say that's current J, is going to get imaged across these metallic walls, right? So like that, and then in this direction, I would get also imaged in this way, right? So the normal component doesn't flip. And by doing that, what you get is an infinite array. All right, so then I could put a port on the end of this waveguide, send the TE10 mode down. It reflects off of the patch antenna, comes back up. I measure the reflected field. I can calculate an S11, and from there I can calculate the reflection phase or the reflection coefficient of this patch, right? Okay. But the TE10 mode is the only mode that we can excite. Not the only mode, but that's the one we would use. And then what's the incidence on this patch, right? Because whenever we do periodic boundaries, we assume a Floquet plane wave or a Floquet mode as a plane wave coming in. But we can't use this waveguide simulator setup to do normal incidence measurements, because these plane waves are coming in at an angle, right? See here, look, if we put the patch here, then this plane wave is coming in at an angle with respect to the normal, this angle, right? And this one's coming in at that angle. So really what you're measuring is oblique incidence of the patch. But keep that in mind when you do your research and you use software to have periodic boundaries and you emulate these infinite arrays, or simulate these infinite arrays, you can do a measurement, or you can consider doing a measurement using a waveguide simulators. All right? So it's a useful viewpoint. And this is exactly how you'd calculate what actual illumination you have. You have plane waves coming in at some angle psi, right? Okay, great. Okay. Let's look at a few quantities, then we'll get into something fun. I did some simulations that we can get to by the end of this lecture where we can really put these equations that we derive to test, right, to use, to make sure, to validate that we understand what they're telling us. So first, we're going to calculate the power density. The z-directed power density can be written as, so we want to know what the power density in the direction of propagation or along the axis of the waveguide, which is z, sz. This is a vector, but we're really interested in the z component of that vector, so it's poor notation. But szmn, this is what your book uses, is equal to z hat sz. So we're looking at the pointing vector in the z direction. 1/2 real part of E cross H conjugate, right? But E in general has EX and EY, and H in general has HX and HY. But we're not interested in the z component, right? Because we only want the z component out of this operation, right? So one of these two fields might have a z component depending on if it's T or Tm. But we're not interested in that because when we take the cross product between this set of fields, we get z. So Ex cross with Hx, or sorry, yeah, Ex cross with Hx gives you nothing, right? But Ex cross with Hy gives you z, and it gives you Ex times Hy conjugate. And then we have y cross with x gives you negative z, so we get negative z Hx conjugate. All right? Good. So for the TE, Mn to z modes, we get the following expression. If we plug in what the TE expansion, TE modes for these electric and magnetic fields are, we get the following expression. And we can then rewrite it in this way, right? So we have this common factor omega mu epsilon squared. We pull that out of this real part operator, and we end up with the following expression. Okay, that's the power density, right? We want to integrate this so that we can find what the power is in the mode itself. Why is this useful, right? Let's say you have some kind of source and you excite the waveguide with that source. You want to know how your power is distributed amongst the different modes, right? So this is a way to calculate that. Okay, so Pmn then is the power in the mnth mode. You integrate over the cross-sectional area of the waveguide, A0, which is orthogonal to z, or orthogonal to the pointing vector that we're interested in, orthogonal to the direction of propagation. And we have as z dotted with ds. Okay, so we integrate from 0 to b, 0 to a, we integrate as z dx dy. Good. So by these kind of identities, if you will, the integral from 0 to a of cosine squared of m pi x over a dx is 0 if m is not equal to 0, and a over 2 if m is equal to 0. You've probably seen these before. Same thing with the sine, all right? So only when m is non-zero do you get a non-zero result. That's good because these in general are a function of m and n, right? But using these integral identities, we can reduce this to single values or calculatable values, right?
Which two ones orthogonal?
Orthogonal. So the TE modes are orthogonal amongst themselves, and the TM modes are orthogonal amongst themselves, right? And then I believe the TE and the TM modes are orthogonal as well with respect to each other. Okay, good. All right, so PMN TE to Z. Okay, so what we're going to do is use those integral identities. We get the following result. A over, so the integration of the sine squared and the cosine squared that were here, right? We had cosine squared, sine squared, we had, and then sine squared, cosine squared, right? But we integrate these by integrating this entire expression as per this integral. And using these two identities, the sine squareds are going to become A over something, right? So here we have this epsilon naught m is an operator, which says that if q, or m in this case, or n, is equal to 1, then, so that will be epsilon 0, 1, means the E0, 1, if m is equal to 1 for the mode of interest, or n is equal to 1 for the mode of interest, right? Then q, it's 1 when q is equal to 0, sorry. Let me start again. Epsilon 0, so you start with the mnth mode, right? Those are the variables for this power, m and n. So let's say TE10. That means m is equal to 1, n is equal to 0. So then you know what m is here and n is here. You go to this little function here, and you plug in what your m and n is, and for this one, we would get epsilon naught, m is 1, so E0, 1. So when q is equal to not 0, when q is not 0, that's equal to 2. So here we would get an A over 2 for the TE10 mode. And then here we have E, or epsilon 0, 0. When q is equal to 0, we pick up a 1, and we just get B here for the TE10 mode. All right? So it's a way to write that in shorthand notation for all the modes. No. Yeah, it's a little operator, a function. It's a common notation for what's called like the Neumann index of summation. If you have a symmetric summation, then you can say, instead of going minus infinity to infinity, I can go 0 to infinity, and whenever q is not 0, because if I go minus infinity to plus infinity and it's symmetric summation, then minus 10 and plus 10 are the same. minus 9 and 9 are the same, right? Everybody has a pair except for 0. So you don't double 0, but so that's the same thing. They use epsilon for that too. Okay, so if we do that, then we have beta x squared plus beta y squared. We know that's beta cutoff squared, so that's here. And now we have this expression, right? We can write beta z multiplied by beta z in terms of this, right? So we have, let me show you, we have a beta z here, and omega eta, or omega mu is eta times beta. So so beta z divided by beta is this expression, I believe. All right? We have that from before. Let me show you. So beta z minus, or divided by beta. See if I could find that. I think it's here. No, here. Yeah. So let me clear all this. So beta z divided by beta. It's you can use this expression here, right? By 2 pi. So you multiply by 2 pi f. If you take this over to here, then you get beta cutoff, right? Because then you have 2 pi f, which is omega, times the square root of mu epsilon, which is beta. And then you can use this expression here in conjunction with that. Or you can calculate it from here. So beta z divided by beta. Let's go here. And this is the slide we were on, right? Yeah. So beta z divided by beta. So if we had beta z here, and that became beta z divided by beta. Sorry, let me clear this. Beta z divided by omega mu is eta times beta. So beta, well, that's equal to the square root of 1 minus, yeah, this is correct. Squared, right? Because beta z is beta into 1 minus fc and then divided by f squared. All right?
And just how do we get that? Or is it, do we just assume it's wrong?
No. These are coefficients. All the coefficients are lumped, right? Now, these will depend on your source. So whenever you have an actual excitation into the waveguide, that has some power that you're launching into the waveguide, and you'll distribute that power amongst the modes like this, and you'll be able to calculate what these amplitudes are. I'll show you how to do that later, next lecture, as a matter of fact. How to expand fields due to probes in terms of the modes, right? We'll solve a coupling problem, which is not in the book.
So if we're calibrating power and also trying to calculate the power, where does it start?
So the first thing you need to do is take your known fields in your source and you expand them in terms of the modes, right? And then from the expansion coefficients of that expansion, you'll know what the A's of each mode are. We'll show you that next lecture. Okay, for TM modes, you get this expression, right? So there's some subtle differences here. In the TE, you have eta in the downstairs. Here you have eta upstairs. Here you have epsilon, but here you have mu. And the other things about the expression for the TM modes is there's no epsilon operator, all right? It's always A over 2 and B over 2. Okay, good. So now, any field can be expanded into a set of TE and TM modes. The total power then is just the sum of all the power in the TE modes plus the sum of all the power in the TM modes, all right? Okay, very good. All right, let's look at attenuation now. All right, so we calculated modes and lossless waveguides that were infinite, and they were filled with a lossless permittivity of epsilon and mu, and the walls were PEC. But now we're going to start adding losses, where things start to get fun, and we'll do some simulations at the end of this lecture in order to validate all of these equations that we're deriving in terms of that describe the losses. So to calculate the losses, one assumes the conductivity is sufficiently high such that the modes are only slightly perturbed from the lossless case. All right? And this is what they call the perturbation method, really. But hence, the modes are assumed to be the same as in the lossless case. We've already derived what the modes look like, the electric field and the magnetic field. We need the magnetic field and the electric field, right? To calculate, we need the current density to calculate the losses. And the current density is related to the magnetic field. So we're assuming that the magnetic field is that of the modes of the lossless waveguide that we've already calculated. And by adding loss, we don't perturb them significantly. It's negligible, right? Slightly perturbed. So the lossy walls are represented as a surface impedance. So we saw this last semester. We have a surface impedance, which is complex as a real and imaginary part, consisting of resistance and reactance. And we found that last semester to be the square root of j omega mu over sigma plus j omega epsilon. Okay, so what happens if we have a lossless medium, right? What does a lossless medium mean? Okay. Infinite conductivity, that's correct, right? So what does that mean for the surface impedance? 0, right? Very good. Good. All right. And what if the medium has no conductivity? Like free space? No, right? So what do we get? The square root of sigma is equal to 0 in free space. So the j omegas cancel, we get the square root of mu over epsilon. So it's eta, right? Okay, good. So for sufficient conductivity, I don't know if you remember, but last semester we said that when sigma is much, much greater than omega epsilon, what does that imply? We have two kinds of currents, right? If we write Ampère's law, the curl of H, as we have J due to conductivity, we have J due to dielectric, and we have, of course, the displacement, right? I think we can write that as J displacement, but I don't want to. Let me not use the same notation for that. So let's just do J displacement for now, right? So we get sigma E plus we get J omega epsilon E, right? And we can factor this out. We get sigma plus J omega epsilon into E. All right, fine. And then we can factor out a J omega. So this is equal to J omega into sigma divided by J omega plus epsilon into E, right? What did I do wrong there? I feel like something's wrong. Sigma J omega epsilon E, yeah, okay. So if you factor out that, you get that, right? Okay, then you can also split epsilon into a complex if you assume that the dielectric also has losses, right? All right, but anyway, this kind of tells you what the origin of these two currents are. You have sigma E and you have J omega epsilon E. This is displacement current. This one is displacement current, right? And this one is conduction current. So if the conduction current dominates over the displacement current, then you can write your surface impedance in this way. Square root of omega mu over 2 sigma 1 plus J. All right, good. So that's the surface impedance for a highly conductive surface, right? Like copper. The power absorbed and dissipated as heat by each of the surfaces in the wall of the waveguide is written as the following. This is similar to like I squared R, right? So J, the integration, 1/2 I squared R. All right? So P power dissipated and conductive losses is RS over 2, where RS is the real part of this ZS. The integration over the cross section of the waveguide, integration over the wall of the waveguide. JS dotted with JS conjugate, DS, right? Where JS is N cross H evaluated at the surface. All right. So what does the attenuation constant tell us? The attenuation constant tells us if we know the power at some point, at a reference point, say Z equal to 0, call that P0, right? The attenuation constant tells us that at a distance of L, the power at that location, in the mnth mode in this case, is equal to the initial power times e to the minus 2 alpha z, right? Because we're talking about power, it's 2 alpha z. All right, so that means that if we know the power at some reference point, P0, say at z equal to 0, for example, so Pmn, the power in the mnth mode at z equal to 0 is P0, and we can find the power at any z in that mode by multiplying by e to the minus 2 alpha c times z, all right? So the negative rate of change of PZ or PMN represents the dissipated power per unit length, right? Why is that? Because if the power is decreasing along the waveguide, then it must have been dissipated in lossy walls, right? We're assuming that the inside of the waveguide is filled with lossless material. So that means that if we have sort of a slope of the power, and then we have a run, then we know slope is equal to rise over run. Then the change in the power is going to be equal to the derivative of the power in the mnth mode with respect to z, right? Times z. And it's decaying, so it's a minus. Does everybody understand this formula? Okay, good. All right, so we evaluate that at z equal to L. So now what we have to do is differentiate our expression for PMN with respect to z. We get 2 alpha c z p naught e to the minus 2 alpha c z. And we evaluate that at z equal to L. We get 2 alpha c L PMN. All right? Now we can solve for alpha c. Yes?
Current on the walls inside it.
Yeah, so what we've done here is we've modeled the wall with a sheet impedance, right? A resistive sheet impedance. And we're assuming that that's impenetrable, right? So all the loss is happening right at the interface due to the way we've modeled the waveguide walls, which is common. If you were to do a simulation of a waveguide in HFSS, for example, then you would do the same thing. You would model those walls with the surface impedance instead of trying to resolve the skin effect is what you're talking about in the waveguide itself, because then the field decays so fast, the skin depth is nanometers, right? And you have to put so many tetrahedron in your metal. So you uncheck the box that says solve inside, right? And you would just put a surface impedance there. Much more efficient. Okay, so alpha C, we solve for alpha C, right? PC divided by L, so here's L, here's PC. So this is PC equals to 2 alpha C L PMN. So we solve for alpha C. Okay, we know what PMN is. We found it, right? A few slides ago. And PC is given here, right? We know, okay, so we know what PC is, right? Okay, good. So alpha C depends on the power dissipated in the conductor per unit length divided by 2 times the power in the mode, right? The expression for that. Evaluated at z equal to L. Okay, let's do some more calculation. So let's take it a step further. Let's consider the dominant mode, TE10. We have the total power dissipated on the walls of the waveguide is PC10 mode now is twice. Why twice? Because we're going to double what we calculate for the bottom wall and double what we calculate for the left wall so that we get the total, all 4 walls. And we know it's the same for the bottom wall as the top wall and the left wall and the right wall. We use our formula, RS over 2, J dotted with J conjugate. All right, the current density on the bottom and left walls can be found here. So this is the bottom wall. We've calculated this already, right, in a previous slide. And for the left wall, we've calculated that as well. So now the losses associated with the bottom, top, and left, right walls are here. The bottom and top walls, we can say is RS, factored out from here, right? We plug these expressions in for the bottom and the top walls for JS bottom. We get RSA 10 squared multiplied by this. And we have these 2 integrals, right? The integral of cosine here and the integral of sine here. Everything else is a constant. We know what those integrals are, right? We've looked at those. We get the following expression here. All right. Okay, and the left and right walls, we get the same thing, right? For this. We get a different thing. But we know the left and right wall only has 1 component. Okay, good. So we get these 2 expressions for the loss. So whenever you derive expressions like this, they might not come to life until you actually do some investigation into them. I ran some simulations and I'm going to show you in CST we get the exact same results using a numerical approach rather than an analytic approach, right? So we'll see those in a second here. All right, so yeah, the derivations we got to are here, but we'll show that they are exactly correct, right? Good, okay. So combining the results, we obtain the total dissipated power by combining all 4 walls. We get the following expression, right? PC10 divided by L, the power that's dissipated into the conductivity of the walls of the waveguide for the 10 mode per unit length L is equal to this expression here. All right, that's just combining the previous 2 expressions. All right, so we almost have everything we need for our alpha, right? Our alpha, we needed PC divided by L. We just calculated that. Now we need 2 into PMN. All right. So here's the PMNTE to Z. We already calculated this in the previous few slides ago. We had this expression, right? Now we can specialize this to the TE10 case. So we can get PE or PTE to Z of 10, and we can calculate the attenuation constant by using the formula we derived by considering what that definition of the attenuation constant is. It's the power at a given location L with respect to a known reference, right? Here's a known reference. Here's the power at Z equal to L is calculated using this formula, P0 e to the minus 2 alpha CZ. By definition, we can calculate now what the alpha is for lossy waveguide walls. All right, it's this expression here. In terms of Neppers per meter, all right, Neppers are kind of similar to a dB, but they're field, they're decays in terms of the field quantities, not the power quantities. And we can make plots of this for different permittivities that are filling the waveguide. So here we have an X-band waveguide made of copper and filled with lossless dielectric of permittivity epsilon. For epsilon equal to epsilon not air filled, we get this curve here, right? And at different frequencies, we can see we get different attenuation constants. So at some point, why do these things have a lot of loss here? Yes, very good, right? Okay, and we have epsilon equal to 4 epsilon naught and 2.56 epsilon naught is the other dash curve, right? We're going to use this curve in some simulations that I'm going to show you in a second, all right? Very nice. Okay. So the attenuation constant for any mode in general, these are the general expressions. We derived it for the TE10 mode. These are the expressions for general modes. You can use these in your research, right? All right, they're there for completeness. So we got to do one more thing. We need to look at dielectric losses. Then we're going to go through some simulations, which are very interesting, all right? All right, so we already took care of the losses. We derived an attenuation constant. Whenever we analyze waveguiding systems in electromagnetic theory, we need to know a few quantities in order to characterize our modes or characterize how to utilize the lines in design. We need to know the input impedance or the characteristic impedance of the line, right? So that we can match to it when we want to feed it. We need to know what beta is so that we can calculate the phase delay with respect to a given length of line, right? And we also need to know alpha. So we need to know the complex wave number and the characteristic impedance of the transmission line. And we've calculated beta already. Now we're going to consider, and then we calculated alpha for conductive losses in the metal walls of the waveguide. Now we're going to look at lossy dielectrics that fill the waveguide, and we'll have our total alpha. Then we'll have beta alpha, and we have the impedance, we have everything we need, right? Okay, so if the waveguide is also, or if it's filled with a lossy dielectric material, an additional attenuation constant can be defined, which is that for dielectric, alpha D. We already calculated alpha C. You just add these two together to get the total alpha, and we'll show later that this is correct. Lossy dielectrics are modeled with a complex permittivity. Remember from last semester, epsilon complex is, so okay, this is attenuation due to conductivity, and this subscript here refers to complex permittivity, but this subscript here refers to conductivity. All right, so don't mix those up. Epsilon prime minus j epsilon double prime. All right, so let's go apply the complex permittivity to our separation equation. Beta z, complex. Now we're calculating a complex beta in the direction of propagation. Is the square root of beta complex squared? So this beta z is complex because this one is complex, right? Minus beta x squared plus beta y squared. All right? Beta c is omega squared mu epsilon complex, right? Now it's complex permittivity. Then we have epsilon complex is epsilon prime minus j epsilon double prime. Now let's combine real and imaginary parts. All the real parts are here, and the imaginary part is there. All right? Let's call all the real parts, or let's call this omega squared mu epsilon prime as beta c prime. And we'll plug that here. And then let's call, okay, so we'll recognize here that sigma effective. I don't know if you remember from last semester in lecture 2. Sigma effective was the static conductivity, sigma static, plus omega epsilon double prime. But here we're considering that there's no static conductivity. So it's omega epsilon double prime, all right? Because we're talking about dielectric here. So we see omega squared mu epsilon double prime. We can pull out one of the omegas, and the epsilon double prime will get omega mu sigma effective. which is here. All right. Now, what we're going to do here is we split this up. This looks like we factored out. Yeah, just factored it out. Yeah. Square root. So if we factored this term out, then it appears down here as well. Okay, good. Why do we write it like that? Why do we want to do that? We're trying to separate this into real and imaginary parts in the end, right? And we're almost there. This is real, that's imaginary. We're probably going to apply a binomial theorem binomial expansion. Okay. So now we're going to apply the binomial expansion. 1 minus x to the alpha is approximately 1 minus alpha x to get rid of that square root. Then we can separate into real and imaginary parts. For x less than 1 and alpha x much less than 1. Okay, so this is the binomial expansion. So beta z complex is the square root of that. And then we have the square roots by factoring that out from the last slide. Okay, so now we have this. We apply the binomial expansion. The 1/2 comes down. We get 1 minus 1/2 x, right? And x was everything in here. So 1 minus, there's the 2 from the 1/2 from the power coming down, and the rest of it remains, yeah? Okay, now we're in a form that we can separate real and imaginary part. So we're almost there. Here, what are we doing here? This looks the same as the previous line. It is, okay, so that's a wasted line there. And then we have the square root of that minus j. So we distribute this into this, right? So this is a repeated part here. This part was repeated. All right. Now we have it separated into real and imaginary. Here's real, here's imaginary, right? Good. Okay, so, all right, let's see what we're doing here. So we recognize these two terms, right? This one and this one. And what we can say here is that we have beta c prime squared minus beta x squared minus beta y squared. So beta c prime, we said, was omega squared of mu epsilon, all right? So we have beta c into the square root of 1 minus fc over f squared. This is what we wrote that term as. Very good. Omega mu sigma 2 beta c squared. So what have we done here? We've said that beta c prime squared minus beta x squared minus beta y squared. Well, that we're saying is equal to beta c prime. And I don't think it should be squared. Square root of 1 minus, one of these has got a typo. And we already said that this was beta z, right? Yeah. So, good. So, this is not squared. All right. Copy and paste there. Very good. Now, beta c prime is omega squared of mu epsilon prime. Yeah? All right. So, and then we get 1 minus fc over f. All right, good. All right, so one more in simplification we're going to do is we're going to define eta prime as a square root of mu over epsilon prime. Remember, epsilon prime is the real part of the complex epsilon. And we can then write this imaginary part as eta prime over 2 sigma effective divided by 1 minus fc over f. What did we notice about this, right? What is the whole point of this? Beta z. Remember, beta z is related to beta c squared of 1 minus fc over f. But now we have some complex numbers here, so we're carrying those along with the derivation. All right? Okay, so what do we notice here? Why do we write it like this? So this is beta multiplied by some frequency dependent term, right? And this is eta multiplied by some eta times sigma multiplied by some frequency dependent term, right? So here what we see is that the complex propagation constant, the direction of propagation, is frequency dependent, right? Dispersive. All right. So I know I can see all your faces. When we go through all of these derivations, step by step of all of these lines, and we get to some expression, it's like, what the heck are we doing, right? There's a bunch of numbers here at this point. It doesn't have any meaning. I mean, it has meaning. You know what it is. You understood the derivation. But let's make it come to life, right? So went through this long derivation. What did we actually learn? So here I've repeated it. What's that?
The square root in the denominator
Hmm.
should be there.
Yeah, this squared, it comes from here, right? This term is the same as this term.
No,
Oh, I see what you mean. Oh, that means that is supposed to be squared. Sorry. Right? This is correct. Let me go back. It's a good thing. Let me go back and check that. I'll let you know.
Shouldn't the square root be on that second red highlighted term? Because you distribute the square root to both parts.
Say again, the
Like
square root.
second red underline, shouldn't that be square root instead of parentheses? The denominator.
denominator should have a square root.
You mean here, right?
Yes.
I don't know though, because here,
You're distributing that square root in the step before.
so this, and then we have, okay, let's double check. That might be.
Should be square
I'd be
root.
surprised if I typed these out with that many typos, so.
That term is wrong.
Here, we factored out the square root of beta c squared, right? So here, let's do it from here. From here, we have the square root. Let's call all this thing x for now. X minus j omega mu sigma, right? All right, if we factor out the square root of x, we can say this is x square root of multiplied by 1 minus j omega mu sigma divided by x, right? Yeah, that's correct. And then we can split this now. So square root of x multiplied by the square root of 1 minus j omega mu sigma divided by x. 1 minus j omega mu sigma divided by x. And x, no, it's correct, yeah?
That term was wrong. If you go.
Okay, but this is correct right here, right? Okay. What's wrong here?
The one that you. That should have. a
This one?
square- Yes. This should have a square root.
Square root is not here. The 1/2 comes down from this, right? So minus this whole thing, which is 1 minus something, becomes 1 minus alpha into x, right? So 1 minus this whole thing is x plus the alpha is 1/2.
I think it's the next step when you distribute that square root term to both parts.
Oh, yeah. This into 1 is that. And then this into this term, right? So we have the square root of x divided by x.
Yeah, it should have a square.
Yeah. So this is really like the square root of x divided by x, which is x to the 1/2. And then we have minus 1, right? And that becomes x to the minus 1/2. Okay, good. That's correct. So this should have a square root, right? That's the correction. Very nice. All right. So then let's see, what does that mean? So these are both square roots. So this is not supposed to be there. That square, yeah? Good. All right, guys. Good catch. That means you guys are following along, which is good, right? You're not tired of the derivations, which you probably are. Let's make these equations, let's make them come to life, yeah? So here, look. Here we have beta zc, we have beta d, we have alpha d, we have separated into real and imaginary part. We can identify a beta d and an alpha d. The beta d we see is the same as it was before. And now we have, and beta d is just due to the epsilon prime of the complex epsilon. And this sigma epsilon contains the epsilon double prime, right? Because sigma effective was omega epsilon double prime. So the double prime of the complex epsilon ended up in the imaginary part as part of alpha, and the epsilon prime, the real part of the complex epsilon, ended up in beta, which we expect, right? That's the whole point of complex epsilon, the loss, the double prime, the imaginary part of complex epsilon that contributes to the loss. So alpha d may be rewritten. All right, so more rewriting. Anyway, you get this expression, right? So let me just tell you. So we take this alpha d, which is the expression that we're after, and we rewrite eta prime as square root of mu over epsilon. And then we have omega epsilon double prime for sigma, right? Okay. The reason we wanted to do that is we wanted this term. I don't know if you've recognized that, but that's tan delta. Loss tangent. Okay. Then this is all, then we're left with the omega square root of mu epsilon prime here, right? So this omega plus the square root of mu here. And then we have epsilon prime here, and we divide. Where do we pick up this square root of? Oh, yeah. So this, we can say multiply by the square root of epsilon prime downstairs and upstairs, right? And then we get epsilon prime. Okay, good. This is beta. this is beta. Then we have beta is 2 pi over lambda. And then we have this expression by multiplying things out, right? And canceling the 2's. All right, then we have alpha d, like this, right? And we can define that here because we see the guide wavelength as this expression, all right? And then there's lambda squared here. We pick up one more lambda so that we get this expression, all right? Now we can also write this in terms of dB. I don't know if you remember, to convert a Nepper per meter to a dB, we multiply by 8.68, right? So epsilon prime, double prime, or epsilon pi over lambda, lambda g over lambda, 8.68 multiplied by the Neppers, you get dB. So this comes out to 27 if you use the pi, and 8.68 multiplied, you get that. All right, good. So this is a good expression here you can use, dB per meter, for your waveguide that's filled with lossy dielectric. Okay, good. So let's look at an example. So I did a bunch of simulations, right? I wanted to make sure that these things made sense. How did I understand them? I went through these simulations to try to correlate it. So an X-band rectangular waveguide is filled with polystyrene. This is a kind of an example in your book, but I also did the simulations, whose electrical properties are at 6 gigahertz are epsilon r equal to 2.56 and tan delta equal to 2.55 times 10 to the minus 4. All right? Good. To determine the dielectric attenuation at a frequency of 6 gigahertz. Okay, so first thing I want to ask you is, this is an X-band rectangular waveguide. What is the frequency range for X-band? 10 to 12. Why are we operating it at 6 gigahertz? It'd be cut off in X-band, right? But that was for what kind of waveguide? Air-filled. So when I fill it with epsilon r 2.56, then 6 gigahertz is a propagating mode now. All right? Okay. So tan delta is epsilon double prime over epsilon prime. They defined that. This is what your manufacturer will give you for dielectrics, like Rogers. Lambda naught, 5 centimeters. So it's 30 gigahertz divided by, or 30 times 10 to the 9 divided by 6 times 10 to the 9. And lambda in the material, in the dielectric, lambda d, is lambda over square root of epsilon r, which is 3.125 centimeter. All right, we need all those numbers so we can calculate what the cutoff frequency, or we can calculate the guide wavelength. But the cutoff frequency first, 1 over 2a squared of mu epsilon, right? All right. And what do we get here? We get, okay, do you remember what this equation comes from, right? It was given along a few slides back. So it's the square root, where is it? Here. So remember, it was Fc of Mn was equal to 1 over the, I think, 2 times the square root of mu epsilon into m pi over a. Let me pull it up real quick. Right, it was here where we studied the z-directed quantities. It's here, right? 1 over 2 pi square root of mu epsilon. Then we have this. But for the 1-0 mode, this term goes to 0. Then we have pi over a squared that comes out as a pi over a. The pi's cancel. We get 1 over 2a squared of mu epsilon. All right? Just so we're there. Okay, good. So that's the cutoff frequency for the 1-0 mode. It's 4.1 gigahertz in an X-band waveguide, the dimensions of X-band waveguide, because we filled it with dielectric, right? All right, great. The guide wavelength is 4.28 centimeter. We needed the lambda g and the lambda to calculate alpha d from the formula we just derived. We plug in all the numbers here. We get 3.511 times 10 to the minus 12 analytically from the formulas we derived. All right? All right, so then, okay, so we get beta c as well. Omega squared of mu epsilon prime gives rise to beta, right? Double prime gave rise to alpha. And we get 201 radians per meter. And the z-directed wave number is beta times the square root of 1 minus fc over f squared. And we know what beta c is from here, 201. And then square root of 1 minus 4.1 divided by 6, we get 146. So I went to CST, I drew a rectangular waveguide. I put waveguide ports on the front and back of it, filled it with this material 2.56 with this tan delta. The color's not showing up well. It doesn't look like that on my slides. But, and then I did the simulation and I calculated what the port mode properties were, alpha and beta, and the S21. So what do we find numerically? Remember, this is a numerical simulation that's doing, I think, finite element is what I chose here. And it doesn't know anything about these analytic formulas. It's not using these, right? It's doing a numerical solution. It finds alpha to be 0.035, same thing we got. And beta to be 146.8, that's what we got. So numerical solver shows that the analytic formulas are correct. Really, the analytic formulas are king all the time, right? You validate your numerical codes using analytic formulas. So this is a nice kind of verification of it's true that these things work, right? But we don't usually calculate alpha and beta. Oh, we do calculate beta and alpha, I guess, but really we want to know S parameters when we're doing simulations like this, right? So can we predict the S parameters from these analytic results? So with the alpha D, we should be able to calculate the value of S21, right? If P naught is the power at some reference point, say Z equal to 0 at this point, at waveguide port number 1, and we have a length of L equal to 1 meter, for example, then at a length of 1 meter, Z equal to 1 meter, we should be able to calculate what the S21 magnitude is by knowing the losses analytically. So PMN at function at a position Z is PNM at Z equal to 0 times this, right? So we know in CST, the power that applied in CST to the port is half of a watt. So we know P0 is 0.5 watts. We know alpha D, we calculated analytically, we verified it using CST is 3.511 times 10 to the minus 2, and we're looking at Z equal to 1 meter, right? If you do that at 1 meter, you get 0.4661 watts. Here's from CST's help guide. It has various powers that it calculates when you do simulations. One is called the power stimulated. That's P0. It sends 0.5 watts into the port. Then the port might not be perfectly matched, so you might reflect, right? Not only do you reflect, but some power could come back out from the other port if you don't absorb it well. Power accepted is 1 minus gamma squared, yeah? So then the power accepted, now that could be radiated or lost throughout the waveguide, right? Or throughout whatever structure you have. So we're looking at the losses. There's nothing radiated because this is an enclosed geometry with metal all around it. So by the time we get the power outgoing, that's going to be power simulated minus the losses. So we go over here to power outgoing, and we find what power outgoing is. We find it's 0.4662, and that's exactly what we calculated, right? So CST is also corroborating our results, which is cool. So what about S21? That's what we want to find, right? So what is S21? S21 in terms of dB is 10 log of a ratio of powers. Power at Z equal to 1 meter divided by power at Z equal to 0. Or power in the input port divided by power at the output port, or S21, right? So S21 magnitude in dB, if you take 10 log of this ratio of powers, we know PMN has P0 in it. So really we're just looking at 10 log of e to the minus 2 alpha dz. All right, so we know our power at Z equal to 1 meter, and our power stimulated, we get minus 0.3049. Analytically and numerically, we see minus 0.303, right? So it's pretty good. So we can, with these formulas that we've derived, we can calculate what the S21 is in a waveguide if we know what it's made out of and what it's filled with, right? And we can calculate its cutoff frequencies. We can calculate the mode propagation, or the propagation constant of the mode. We can calculate the modal profile. The only thing left we don't understand is how to excite the waveguide and how to describe the mode distribution, or the power distributed between the various modes in terms of the excitation, right? That's what we're going to do next lecture. But we've understood now how to calculate all of these propagation constants, all of the characteristics of a guided wave, right? Okay, one more thing. We added conductor losses now, because before that was dielectric loss. So now we have polystyrene inside, 2.56 with tan delta 2.55 times 10 to the minus 4, and the walls of the waveguide are made of copper, all right? So we have both kinds of losses. Let's verify both our alpha D and alpha C and see if CST gives us the same result. Alpha C, the formula we derived, right? We got to the end and we're like, oh my gosh. Let's see. We have this formula. We know what RS is. RS is the square root of omega mu over 2 sigma, the real part of Z, right? They were both the same. They were out of phase by 90 degrees. Omega, square root of omega mu over 2 sigma into 1 plus J. So the real part is RS, 0.0204 ohms. So we can model the copper waveguide walls as sheets that are impenetrable, that support surface currents, that have a resistance of 0.0204 ohms. Pretty good, right? 0.02. All right. We plug that into this formula, which I've expanded here with all the numbers that we derived. We get 0.0165 nepers per meter. We add that to our dielectric attenuation constant of 0.035, and we get the total of 0.0516. Redid the simulation in CST with copper and polystyrene, and we get the new alpha as 0.0515. which is exactly what we've calculated numerically or analytically. So the numerical solution is also, it's a little off, right? I mean, these are exact, they're analytic formulas, but the numerical solution is close. The power at Z equal to 1 meter due to both conductor and dielectric losses now is the alpha total instead of alpha C or alpha D. And if we use this alpha total here, 0.0516, we get 0.451 watts out of the 0.5 that we sent into the waveguide at the output at 1 meter away. 1 meter is kind of a long waveguide, right? The wavelength here at 6 gigahertz was, what was the wavelength here? 6 gigahertz, 3 centimeter, right? So we're talking about 1 meter versus 3 centimeters, a long waveguide. Okay. Anyway, this is the power outgoing the next slide. So we calculate 0.4510 watts. We go down here, we get the same number power outgoing on the port, including dielectric and copper losses. Our analytic models based on this alpha total versus the numerical model, which is calculating based on a finite element method. What is S21? If we include both these losses, we can calculate this analytically on paper. We don't need the numerical tool, but it's cool to see that it gives you the same result. Now it's 0.4510 divided by 0.5, 10 log of that, negative 0.4479, half a dB loss. And we get the same thing, 4458, yeah? So that's good that we see the same result in numerical simulation, gives us confidence that our results that we derived are useful, first off, and that they're correct, right? Okay, so when you do a derivation yourself, you need to verify it some other way. So use the numerical tool and say, okay, I got the right result, right? I didn't make a mistake in my derivation. Or if you have a derivation that you believe is correct, then you can use that to validate a numerical tool, right? Always have some way to check your results at the end to make sure that you got something correct. Because if you go too far with the wrong results, then you may make mistakes. Okay, so this is just a prelude to what we're doing next lecture. We're going to expand mode. We're going to expand electromagnetic fields in the waveguide in terms of a superposition of modes, which are orthogonal and satisfy by doing an eigenfunction expansion. All right, we'll do that next on Wednesday. Any questions? All right, good. All right, see you guys. It is time to end, right? Yeah.
Could you explain again what the surface is when the conductivity is zero? I didn't really catch that.
Yeah, so when the conductivity is 0, then sigma is equal to 0. So let's go back to that. I'll show you. When the conductivity is 0, so it's kind of a bad model for 0 conductivity, right? But if the conductivity is 0, then you have the square root of j omega mu divided by j omega epsilon. And then the j omegas cancel, you get the square root of mu over epsilon.
Oh, gotcha.
And that's the same as the wave impedance of free space, right? Because free space is a lossless medium.
Right.
So whenever you introduce a non-zero conductivity, so if I have a dielectric media that has loss, then this would be the formula for the wave impedance, right? You introduce sigma. In last semester, we had some lectures on that. If you want to review them, they're on YouTube.
Yeah, you sent me the playlist.
Oh yeah, good. Oh yeah, how's it going, man?
I feel like I'm keeping up 70%.
Yeah?
I'm with it. There's some things that I just haven't learned or haven't seen.
Okay.
Other than that, it's
Okay, yeah. Do you want
I think
to?
I'm doing okay.
Yeah, you'll be fine.
Yeah, you think so?
Yeah, so anything that you're not getting in a lecture, go to those or ask me. I can clarify it for you. I'll spend extra time with you answering questions and all that. Come by the office hours with any doubts you have and we'll clarify them all.
Cool.
And then their lectures from last semester will definitely help.
Yeah.
And when
I'm writing down everything that that I just don't know what it is.
Yeah, that's a good idea. Yeah, don't leave those unanswered. Make sure you get those questions answered because, once you don't understand something, then later on it becomes too many things you understand and you start getting lost and then you lose motivation.
One thing that I think is probably quick is that F and A versus E and H. How are those different?
Yeah, okay, so I would watch the YouTube lectures on chapter 6. 6. Those are critical lectures. You're going to need those for the rest of the semester too, because we're going to do integral equations founded on those.
Okay.
So that's how you calculate radiation due to current distributions.
Okay.
Those are probably the most important things to watch out of that whole playlist. It's lecture 6, but I don't know when that starts in the lectures, probably somewhere around like lecture 14 or something.
Okay.
Yeah, it's radiation due to current sources and stuff. Very important.
There's a lot of stuff that I would have thought was covered in 3105 and 6, but that just isn't.
Yeah, these things, you have to see them like from different people's perspective and see them multiple times. Really even work with them before you really like, before it clicks, right?
Oh, yeah.
It took me a long, that's, one of my colleagues here said that the hard part about electromagnetics is it takes a long time to get into,
Yeah.
but then you're valuable, right?
Yeah.
Not too many people have patience for that.
Oh, yeah.
And then you're one of the people that know things that a lot of people don't.
Yeah. Dr. Mantegi said something just like that today.
Yeah. Make sure that, but don't feel discouraged, do your best to understand it at that point. But you're gonna need to see it multiple times.